Hello, everybody again. Good job so far. I'm impressed. You guys are doing great, hanging in there with the whole COVID-19 freak out. E-learning extravaganza, spring 2020. All right, we are going to talk about next how voltage works through a circuit, how voltage drops. So voltage in a circuit. All right, so if you remember correctly, voltage is a ratio of, or it's the relationship between current times resistance. This is Ohm's law. We put that in a triangle like this, it would be on top. IR. And the real deal here is that I is a function of your voltage and resistance. What that means is that you can't just go get some current. You can go get some voltage. You can get a voltage source and a battery or a wall outlet, and you can get a resistance. You can get a resistor, which is a light bulb or your cell phone charger, your TV or whatever. So if you push a voltage through a resistor, a certain amount of current will flow. So current, really, we should think about this, is the relationship between the voltage pressed across a conductive surface and the resistance of that material. All right, so if you remember properly, here, put together, you have a battery like this. If this is the positive end, put a little plus here, minus there. That means that there's lots and lots of electrons all crammed together very tightly down here. And we know they want to get away from each other, right? And then there aren't as many up here, which means we have a very high potential up here, potential for being pushed. And you have a very low potential for being pushed on this end. So that means is if you connect this end to this end with a wire or a conductive path, the electrons will then flow very quickly throughout this until they're equally spread out. And electrons will flow until evenly spread out. At that time, we would say the potential for being pushed is the same all the way through the circuit. If that happens, which way do the electrons flow? Let's say if it's pushing just as hard over in this area as it is in that area. You got it. They won't flow at all. No flow if potential is the same on either side of a resistor. And when I say resistor, I mean like a light bulb or a toy or a toothbrush, electric toothbrush. So you can think about it kind of like a door. You get a door here. You got somebody on this side that's pushing on the door, trying to move it that direction. And somebody on this side who's approximately the same size is also pushing on the door in that direction. The door is not going to move. But if you have more push on one side than you do on the other, then the door will move. So it's the same thing with electrons. So if you go up to this drawing, if the electrons are evenly spread out, you're going to have an equal push that way as you do that way, nothing flows. But if you have a difference in potential, that is called a voltage. All right, so we've talked about that before. I just thought it was worth reminding you. So voltage in a circuit. This is where you're going next. We can put numbers on this stuff. So we have symbols. Voltage source looks like this. A little line and then a big line. You put it in a circle like this. And then the wires will go out and go through whatever they go through. So this is a voltage source. That's a battery or something. All right. The wire is just the lines. That's obvious enough, hopefully. And then the resistor, this is weird. You got to get used to this. We abbreviate like this. That's what a resistor is. So a full circuit would look like this. Voltage source, wires, bzz, one resistor, and then back to the voltage source. So here's like your battery, here's your wires, here's your light bulb, and then this goes back over. That symbol we use for any appliance, anything. It could be your hair dryer, could be your dishwasher, could be, I don't know, anything that you plug in or use a battery for, we'll represent it with that symbol. Are you hanging with me so far? Okay, so now what we got to figure out. Okay, so now what we need to work with is, hello. Let's go down here a little bit. Is how does voltage change in a circuit? Okay, so some things we got to know is that in a circuit, you know, this thing is drawn like this. We know what it represents. We just talked about that. But this side over here really represents sort of like a battery in the simplest case. So we say it's positive and negative. And then what we know, remember how we talked about all the electrons are all bunched up on one side? We say there's a huge voltage difference there. There's a potential drop, a difference in potential. Well, now it's time to talk about this in terms of numbers. Let's see this battery is a 9-volt battery. That means the potential on the top side is 9 volts. It will drop from 9 volts to 0 volts at the bottom. Now you might think, well, wait a minute. Aren't all the electrons down there? Wouldn't that have the higher potential to push? And I'd say yes, but this is where we can blame Ben Franklin again, because we consider the movement of electrons to be the opposite direction of current. We always say that current flows from positive to negative. That's weird. It's this pretend magical unnegative stuff. So we pretend it's positive. Sorry for the confusion. It's just the way it is and the way it's always been. It's positive charge that flows, is what we pretend. So you might want to say it's higher voltage down here because this is where all the stuff is, and it's lower up there. And you're right in terms of electrons, but in terms of this pretend positive charge, we say that it's got a positive 9 volts at the top and a 0 volts at the bottom. If all the electrons could go all the way through, they'd get to a 0. It's like falling from a high place to a low place. So that's what matters. So what we got to figure out here is what happens to it. What happens as it goes from 9 volts to 0 volts? Well, it gets used in this one lonely resistor here, in this one light bulb. So if it goes from 9 volts to 0 volts, we got to figure this out. If it's 9 volts here, I'm going to represent this with red. And I'm going to say that 9 volts is red. That means high potential. But remember, this is all conductive wire through here, so there's nothing keeping the electrons together. As long as it's all just nice conductive wire, those electrons will spread out as much as they can through that wire, and they all have the same potential. So it's 9 volts here, 9 volts there, 9 volts there, 9 volts there, 9 volts there. But now they get to this resistor, and they can't just easily, charge can't easily go through it. So it's not going to be the same on the other side. It's going to take some work to get through there. Now let's go to the opposite side over here. They say that the lowest voltage is always going to be blue. So this is your 0. So 0 is down here. This is at the bottom of the battery. If you get to there, you're at the lowest place. It's like the bottom. But remember, this is one conductive wire too. So if the voltage is, or the potential is 0 here, it's the potential everywhere in this conductive piece of wire, because the electrons can flow super freely through there. So whatever the potential is in one place in a conductive wire, it's the same everywhere. So what that tells us is that it's 0 volts there, 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 0 volts there. And now we get to this concept, well, wait a minute. How much does the voltage drop across this one resistor? Well, in this one, we'd say that, sorry, that's supposed to be a bracket, not a 3. Let me just get that out of there. So we would say in this one, the change in potential, the change in voltage, is 9 volts, because it goes from 9 volts to 0 volts. And the color coding helps us work that out. Okay, you might be thinking, wait a minute, I don't get it. Why bother with the color coding and all that? Isn't it pretty easy? If there's a 9 volt difference in the battery, and you got a resistor in there, it's got to drop from 9 to 0, right? You got one resistor to use all that voltage up. So all the volts have to go from 9 to 0 against that 1. Well, let me show you something more complicated. Here's the same 9-volt battery. Here, let's say we go, there's one resistor. There's a second resistor. They're both the same. So now let's do this. Where is it? This is 9 volts, which means 9 volts, 9 volts, 9 volts, 9 volts, 9 volts. This is 0, which means 0, 0, 0, 0, 0. Let's do the color thing to help us organize our thoughts. So this is all high voltage, only till you get to that resistor, because it's going to take some work to get the current across that resistor. Meanwhile, we know this stuff down here is the lowest voltage, it's 0. So it's going to go 0, 0, 0 all the way through this conductive path until it gets to the resistor, because it's going to take some voltage to get across that resistor. So this begs the question, what is it in this part of the loop? It's got to go from 9 to 0, but now it has to do it in 2 chunks. So it needs to go halfway through in this one, and then the other half the way down there. So what's halfway between 9 and 0? That's right, 4.5, 4.5, 4.5. And what color in the old Roy G. Biv is right directly between red and your violet? Green. So we would color these ones in the middle green. And this color coding helps us figure out that it goes from 9, loses some to get to 4.5, stays 4.5 till it gets that resistor, loses the rest to get to 0. All right, that's going to get you started. There's going to be some more complicated versions. I guess I can show you that right now. Why not? Let's go back to black. All right. Let's say we have our 9-volt battery. Let's say we do this. This is a different kind of circuit. What's different about it? Some of you guys know the names of this. Some of you have never seen it before, and that's okay. Well, this is called a series circuit. One on top says one loop. Whatever happens in one of those has to happen in the other, as far as current flowing through. Over here, though, you've got more than one loop. See how it can go, or it can go all the long way around. It can go through here, it can go through there. That's 2 loops. That's called a parallel circuit. So let's do the color code thing down here. We've got 9 volts again. So check it out. 9 here is its highest. Up there, everywhere it can touch. Is there anything stopping it at that corner and then a resistor slowing it down? No, man. So you got to go until it hits something. This is still a conductive line. Got to go until it hits something. There. So it's 9 volts all the way across. 9 volts everywhere. What about the bottom part? Let's get some blue going. 0. You know, 0 because that's the other side of that battery. It's going to be 0 wherever these conductive lines touch until it hits something. Let's go all the way through here. Hey, so now it's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So what's the drop across this resistor? Well, 9 to 0, that's 9 volts. How about from this resistor? From there to there is that's also 9 volts. So check it out. What do you notice is the delta V here, as we go in series, it went from 9 to 4.5. How much did it change? 4.5 volts is what the change was across that resistor. How much is it from 4.5 to 0? Also 4.5 volts. So check it out. In a series circuit, the 9 volts is split between 2 of these. It's going to lose half of its voltage, half of its push, half of its potential in one, the other half in the other. But in a parallel circuit, it's going to have the same push on either side. This one is going from 9 to 0. This one's going from 9 to 0. Which bulbs do you think will be brighter? The bulbs in a series circuit or the bulbs in a parallel circuit? Give that some thoughts, my friends. And for now, it's time for you to do the concept builder, which comes after this, which is color coding resistance. All right. Thanks for sticking with it, guys. You're doing great. Do your concept builder. I'm going to get you some practice problems coming up soon. All right. Hang in there.